Good afternoon. So today we're going to continue our discussion in chapter 2. We'll start now our discussion in module number 2, which is about introduction to combinational logic. The subtopics in chapter 2 are module 2, 2.1, the design procedure in combinational logic circuits, 2.2 about adders and subtractors, 2.3 is about code conversion. These are conversion between, for example, BCD code and other binary codes. 2.4 is about encoders and decoders. 2.5 about multiplexers and demultiplexers. 2.6 about comparators, and lastly 2.7 HDL models of combinational circuits. So that will be the coverage for module number 2, Introduction to Combinational Logic. Let's go to 2.1, Design Procedure in Designing Combinational Logic, the procedure in designing combinational logic. Introduction. Logic circuits for digital systems may be combinational or sequential. So there are two common types, combinational and sequential, when it comes to digital logic circuits or systems. A combinational circuit consists of logic gates whose outputs at any time are determined from only the present combination of inputs. That is for a combinational circuit. The output depends only on the present combination of inputs. In contrast, a sequential circuit has outputs that are a function of the inputs and the state of the storage elements. That is for sequential circuits. We will discuss combinational circuits in this section. So let's discuss first combinational circuit in module number 2, and then in module number 3 we'll be discussing synchronous sequential logic circuits. Objective for this module to apply the steps in for this section. We'll try to apply the steps in designing a combinational logic. First, let's differentiate combinational circuit and sequential circuit. In combinational circuits, the components are logic gates whose output at any time are determined from only the present combination of inputs, while for sequential, they employ storage elements in addition to logic gates. So this is the key word for sequential circuits. They have storage elements. Aside from the logic gates that is also present in combinational circuits, they have additional storage elements. Combinational circuits perform an operation that can be specified logically by a set of Boolean functions. So all those Boolean functions that we have studied from the previous modules or sections, those are forms of combinational circuits. Excuse. Let's recall, for example, all those functions. For example, f equals x prime y plus y z, is equal to x y z plus x prime y prime. These are Boolean functions, examples of Boolean functions, and this represents combinational circuits. If we try to draw the logic diagram equivalent of these Boolean functions, the resulting logic diagrams are combinational circuits. No storage elements, so they are not sequential circuits. The output for the sequential circuit, the outputs are functions of the inputs and the state of the storage elements. So we will discuss this later, the sequential circuit. Combinational circuit, this is an interconnection of logic gates. While sequential circuit, the outputs of a sequential circuit depends not only on the present values of inputs, but also the past inputs. So there's a sort of, if we have this circuit, and we have the output, say Y, there's a feedback, something. Aside from the storage elements, we also have a feedback path for the sequential. For the combinational circuit has logic gates with no feedback paths or memory elements. While for sequential, circuit behavior must be specified by a time sequence of inputs and internal states. Usually sequential circuits have clocked. This has a clock input that will be the basis for the timing sequence. Combinational circuit, this consists of an interconnection of logic gates. Logic simulators show only zeros and ones, not the actual analog signals. Yes, we have already discussed what these logic simulators are. So we don't really, but we know that the output waveform of a logic simulator, something like this, 1, 0, for example, 0, 1. So we specify the output as either 0 or 1. We don't actually care or specify that this is 5 volts or this is 0 volts or 3 volts. We are just looking at the logic output of the waveform of the signal, which is either 0 or 1. Standard cell in complex very large scale integrated circuits, or VLSI. These are circuits that are employed extensively in the design of digital systems, perform specific digital functions commonly needed in the design of digital systems. Examples of standard cells are adders, subtractors, comparators, decoders, encoders, and multiplexers. So these are examples of standard cells. There are many companies that provide standard cells aside from the common logic gates like the AND or etc., exclusive OR. So these are part of the basic standards, primitive cells or standard cells that some companies sell in the market. They are called vendors, usually called vendors. They sell to who are their target market? Other design companies. that design these ICs, digital or analog. They sell their technology, standard cell technologies, to these design companies. This standard cells can the standard cells have this basic logic gates, and then the additional digital standard cells like adders, subtractors, decoders. These are also considered as standard cells. Depending on the package of their product, they will specify what standard cells they have in that package. The diagram of a combinational circuit has logic gates with no feedback paths or memory elements. Yeah, if we check our previous modules, diba? For example, this is just, we know that this is an example of a combinational circuit. This is an AND gate, X, Y. Then we OR that with Z. RF is X, Y, or Z. From this diagram, we observe that there is no feedback path. We don't show something like this. There's no such thing for this function. So the output F is only a function of X, Y, and Z. There's no feedback path going to any part of the circuit. That's why this is a and there's no storage element. That's why we consider this as a combinational circuit. Design procedure. Design procedure for combinational circuits. The first step is, from the specifications of the circuit, determine the required number of inputs and outputs and assign a symbol to each. So we need to determine the required number of inputs and outputs. So number one step is the specifications. Number two, derive the truth table that defines the required relationship between inputs and outputs. Third is obtain the simplified Boolean functions for each output as a function of the input variables. The number four is draw the logic diagram and verify the correctness of the design, manually or by simulation. Let's just make this discussion fast. So step one, specifications. For example, our specification is to design a BCD to XS3 code converter. So BCD to XS3 code converter. We will draw the truth table given the problem. We'll write the inputs and the outputs. Our input is BCD, so this is a 4-bit BCD. We know that a BCD, or binary coded decimal 8421 code, these are the codes. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, same as binary actually, but if we have BCD is the same as the binary equivalent if we only have 4 bits. Binary coded decimal, but if we have one decimal bit, one decimal digit, this is the same as the binary. 1 to 9 is just 0001, and 9 is 1001. But if we have two digits, two BCD digits like 25 in BCD, so this is decimal. Binary and BCD. BCD is same as the binary. If we have one decimal digit, but if we have 25, decimal 25, if we convert that to binary, what is that? Need a calculator. Let's try to convert 25 to binary. Divide by 2. 24, that's 12. Remainder 1. 12 divided by 2, that's 6. Remainder 0. 6 divided by 2, that's 3. Remainder 0. 3 divided by 2, that's 1. Remainder 1. 1 divided by 2, that's 0. Remainder 1. And we read it downwards. So the equivalent of 25 in binary is 1, 1, 0, 0, 1. Let's check. If we convert this again to decimal, that's 1 times 2 to the power 0, 1, 2, 3, 4. 2 to the power 4 plus 1 times 0, 1, 2, 3. 2 to the power 3 plus 1 times 2 to the power 0. So 2 to the power 4, that's 8 plus 2 to the power 3, 2 times 2 to the power 4 is 4 times 4, 16. Okay. So 16 plus 8 plus 1. It's 2. 4 times 4, 16 plus 9. So 9 plus 16 is 25. So correct. So the binary equivalent of decimal 25 is 1, 1, 0, 0, 1. But if you convert that to BCD, that is just 8 bits, which is 0, 0, 1, 0, and then 0, 1, 0, 1. So binary is different from BCD if we have two digits, if we consider two decimal digits. But here, since this is for a single digit decimal, digit, we have 4 inputs, 4 BCD bits. This is the code 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the output x3 code. This is the binary equivalent, binary bits for, these are the bits for the x3 code. And our input is this ABCD. The output is the 4 bits WXYZ, which is the x3 code. That's how we convert from BCD to x3 code. Third step, since we already have the truth table, this is our truth table. We have listed the inputs and the corresponding output. We will now obtain the simplified Boolean function for each output as a function of the input. One way is to apply to use the Carnot map or K-map. For input, we have 4 inputs, therefore we will use the 16 bit 16-bit Carnot map. A, B, C, D, write down the corresponding minterm boxes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Recall the ordering of the minterms in using the 16-bit K-map. Then we need 4 K-maps because we have 4 outputs. For each output, we need a K-map. The first K-map here is for output, is this W? The first K-map here is for Z, the output Z, and then Y, this is for Y. This is for X, and then for W. Let's go to Z. Z is 1 for minterms 0, 2, 4, 6, 8. 0, 2, 4, 6, 8. So we will put 1 to the K-map where the output is 1. So 0, 0, 1, 2, we'll write 1 here, then 3, 0, 1, 2, 3, leaves blank for 3, and then 0, 1, 2. Okay, let's copy this. Let's annotate. This corresponds to minterm 0. This corresponds to 0, 1, 2, 3, 4. This is minterm 4, 5, minterm 6, minterm 8. So 0, minterm 0 here, minterm 2, then 3, 0, 1, 2, 3, then 4, 5, 6, 7, 8, 7, which is 0, and then 8, which is 1, and then the rest is 0, 0, 0. Actually here it should be from 1 to, we should have 1, 0 here, and then up to 1, 1, 1, 1. But it did not include it because BCD has no such input. BCD 4 bits, it should be from 0 to 9 only to represent decimal numbers. The corresponding output here will be the corresponding output with this input. Just don't care. We don't care about the output if the inputs are invalid. So it just, that's why it wrote down XXX. The rest are, yeah. The rest are just don't care conditions. After this 9, min term 9, 8, 9, it wrote down don't care conditions. Min term 9 is 0. This is 0. For the rest, for 10, 11, 12, 13, 14, 15, it's don't care. We don't care. Those are don't care conditions. So how are we going to simplify? Our only concern is all those with number 1. We need to cover all with number 1. Since this is don't care, you can assume it's 1, so this can be considered, and this. Or we know that we can combine the two. They are considered adjacent if they are on the edges. And what is that? A, B, C, D. This is D. What is common to these two rows? It's the 0, which is D equals 0, right? These two are D equals 0, or if you write it in function form, that's D prime. D prime, so Z equals D prime. So I wrote here Z equals D prime. The common is, but this is row 1, 0. This is 0, 0. The common is the last term 0. And that corresponds to CD. The D. D is equal to 0. And D is equal to 0 if you write it in function form, that's Z. The output Z. This is for the ZK map. So Z equals D prime. We already have the output for Z, which is D prime. How about for Y? For Y, this is min term 0. So right here, 1, min term 0, 0, 1, 2, 3, 0, 1, 0, 1, 2, 3, then 0, 1, 2, 3, 4, that's min term 4, 5, 6, 7, 8, 7, 8, 4, 5, 6, 7, then 8. Then for 9, it's 0, 0 here. For 10, 11, 12, 13, 14, 15, that is don't care. Don't care. So we just need to cover the ones. This. We need to cover this, 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 and this. Since this is don't care, we can consider this as 1. Then, how can we cover this? These are also don't cares. Can use this. So there are many ways where we can simplify this function. But I think this is the best, because if we cover this, if we try to cover this, no, it's 0 here. It's don't care, so it's not possible. And what is the equivalent function? What is common? Since this is the entire row, this is for Y. It's equivalent to CD equals 0, 0. So y is equal to c prime d prime. But this, its cd is equal to 1, 1. So we add or here, c, cd. So y is equal to c prime d prime plus cd. That's why we have this function y is equal to cd plus c prime d prime. So that's how we calculate, that's how we use K-map. So we already have the equivalent functions for y and z. The same procedure goes to x and w. You can follow the same procedure for x and w. The output is x is equal to b prime c plus b prime d plus bc prime d prime. And for w, that is a plus bc plus bd. Then we write down the equivalent Boolean functions that we obtained. And then the last step, step 4, is to draw the logic diagram and verify the correctness of the design, manually or by simulation. By simulation, we can use Verilog, write down the equivalent functions, and then assign inputs using test bench. We draw the logic diagram based on the Boolean function for z. For example, for z is equal to d prime, z is equal to d prime. We just use the inverter. For y, we have cd plus c prime d prime. We use OR, and then OR of the AND between c and d, then d prime. So it depends on you whether you will use here. It used an inverter and an OR gate because it will be common to both c plus d. C or d is common to both y and x. Y, x, and w. You can do it this way, just like what is shown here, or you can use inverters and an AND gate. So it's up to you. Anyway, the actual software tool will do it automatically. But what is shown here is the steps on how we convert, how we design from the specifications to drawing the logic diagram. In designing our logic circuits, combinational logic circuits. For subtopic 2.2, adders and subtractors, let's try it. Our objective is to design adders and subtractors using logic gates. Digital computers perform a variety of information processing tasks. Among the functions encountered are the various arithmetic operations. The most basic arithmetic operation is the addition of two binary digits. In this section, we will discuss different binary adders and subtractors, including half adder, full adder, binary adder, carry propagation in adder circuits, binary subtractor, and the concept of overflow, as well as decimal adders. So let's discuss what is a half adder. This is a combinational circuit that performs the addition of 2 bits, while a full adder performs the addition of 3 bits, 2 significant bits, and a previous carry. So a half adder let's call it H. For example, our half adder is just X or Y. For a full adder, X or Y or Z. See the difference? For the half adder, we only have 2 inputs, 2 bit in 1 bit, 2 1-bit inputs, X and Y. But for the full adder, we have X or Y or Z. X or Y or Z, and the Z is our carry from the previous adder. Half adders can be employed to implement a full adder, as we shall see in the next sections. Binary adder subtractor. This performs the arithmetic operation of addition and subtraction with binary numbers. So how are we going to implement the half adder? What are your expected output for a half adder? We know that the output has carry only when both inputs X and Y are 1. So this is a truth table for the half adder. We have 2 inputs X and Y. So we write down the inputs X and Y, and then for the other column, the output will be the carry and then the sum. So we write down all the possible combination of inputs from 0 to 1, 1. So 0 plus 0, we know 0, then 0 plus 1 is 1, 1 plus 0, 1, then 1, 1. The sum would be 0, and there will be a carry of 1. If we convert this to the function or Boolean function equivalent, we can use Karnaugh map. We can use Karnaugh map, or just by looking at this, S is 1 when we just add the minterms. When X is 0, when C is 0 and S is 1. I don't know. S is 1 when X is 0 and Y is 1. And that, if we convert that to the function minterm form, that's X prime Y. Then S is 1 again if X is 1 or Y is 1, Y is 0. That corresponds to the minterm X, Y prime. For C, C is 1 only when X is 1 and Y is 1, which is equivalent to the minterm X, Y. Then we already have the function. If we convert this function to the logic gate equivalents, S, we have OR, we OR X prime Y, so X prime Y and then X, Y prime. We can do it this way, or we can have the input X and Y and then add an inverter here. instead of y prime here. For C is just the AND of x and y. Another way to write this down is to implement this one is to use exclusive OR. We know that x y prime plus x prime y, this is equivalent to the exclusive OR between x and y. So we use the symbol instead of this. So these are equivalent. Let's go to the full adder. Full adder is used in implementing an n-bit binary addition. It has 3 inputs, 2 bits from each number and 1 bit for the carry from the previous bit addition. As what we have already discussed, the full adder has 3 inputs. Z is considered, the third input is considered to be the carry. Either of these 3 inputs is the carry from the previous adder. And then the output is the same. It has a carry and then a sum. So it will be from 0 to 111. There are 8 possible combinations. Then we add each bit 1, 0 plus 1 plus 0 is 1, carry is 0, then 0 plus 1 plus 1 is 1, 0, the sum is 0 but the carry is 1, right? 1 plus 1 plus 1, that's 1, 1, carry and sum are both 1. So in simplifying this one, it is better to use a K-map. For we need 2 K-maps for the 2 outputs C and S. For S, we have 0, 1, min term 1, min term 2, 0, 1, 2, 3, 4, min term 4, 5, 6, 7, min term 7. So we will write 1. Recall that for an 8-bit K-map, this is min term 0, 1, 2, 3. So 0, 1, 2, 3, then 4, 5, 6, 7. That's the ordering. And then we write 1 to min term 1, 0, 1. 2, 3. Write 1 to min term 2. Then write 1 to min term 4, 5, 6, 7. Then 1 to min term 7. So how are we going to simplify this one? There are no adjacent. So there are no adjacent. But there are no don't care conditions also. So it's as is. We can't simplify this any further. Since this is 0, 0, 0 and they are not don't care conditions, so we can't combine. That's just how it is. We write down the min terms. We know that min term 1 is min term 1. This corresponds to x, y, z equal to 0, 0, 1. So x, y, z, we need to add complement to those with 0. So x prime, y prime, z. X prime, y prime, z. Then for min term 2, that's 0, 1, 0. x, y, z equals 0, 1, 0. That corresponds to x, y, z prime, prime. So x prime, y, z prime, x prime, y, z prime, and so on. For C, we have mean terms 0, 1, 2, 3, M3, 4, 5, 5, 6, and 7. So 0, 1, 2, 3, 4, 5, 6, 7. And we know that we can combine this and then this and then this. Recall that we can't combine this 3, but instead this 2 and this 2 should be factors of 2 because we will look at the common variables. So we're expecting 3 terms here. The first term is this column 1, 1 for yz equals 1, 1, and that is yz. For this one, that's y is equal to 1, 1, and then x is equal to 1, so xy. Then for this one, this is the common is z is equal to 1. This one and this one. Z is equal to 1, and then x is 1. So xz. So we OR these 3 terms. So xy or xz or yz. So we have solved for S and C, the outputs of the full adder. Then we draw the logic diagram. This is the equivalent logic diagram for S and C, the outputs of the full adder. Exclusive OR. S is the exclusive OR of is the OR. S is the OR of each of the mean terms, these mean terms. We can draw it like this with x prime and y prime and z prime, but the right way is to have the inputs x, y, z and then add inverter for each of those with x prime. For C is just the sum, so we use OR gate, then AND gate for each of xy, xz, and yz terms. We can see that this can be implemented using 2 half adders and an OR gate. What was the circuit for the half adder? This is the half adder. Recall this, try to remember. Let's write down. For the half adder, we have S is equal to X exclusive OR Y, and then C is equal to XY. That is XY prime plus X prime Y. For the full adder, S is equal to X prime Y prime Z plus X prime Y Z prime x y prime z prime plus x y z, and c is equal to xy plus yz plus xz. Now this is the equivalent implementation of a full adder with two half adders and an OR gate. So it replaces the circuit with two half adders. First adder and then the second half adder with an OR gate. First part, we have only x exclusive OR with y, then the carry is xy, then it is connected to another half adder exclusive OR with the z, and then this is ANDed with the z. Since as for the full adder, we can write it down as x prime y. Where is that? X prime y. X prime. Wait. So x y prime. Then we exclusive OR that with z. We know that this is x prime y plus x y prime. This will be a long process. Z prime plus z times x prime y plus x y prime prime. X prime y z prime plus x y prime z prime plus z times, using the Morgan's theorem, x what is this? Let's not get confused. Using the Morgan's theorem, we have x or y prime, then multiply by x prime or y, right? We use multiplication, and operation instead of or, and then is this right? We complement each, so we complement this. Let's not go to the shortcut so that we will not be confused. So x prime y, we will use multiplication instead of, and then we invert this. We invert each term. So x prime y z prime plus x y prime z prime plus z times, this becomes x or y prime plus x prime or y. Let's try to simplify this just to prove that they are both equal. zx plus zy prime x prime plus y. Distribute this here. Let's distribute. Becomes x prime x z plus x prime y prime z plus x y z plus y prime z. But this is equal to 0. This is equal to 0. So what is left is x prime y z prime plus x y prime z prime plus x prime y prime z plus x y z. So are they equal? X prime y prime z. X prime x y prime z prime x y prime z prime x prime y z prime x prime y z prime x y z then x prime y prime z. So they are equal. The full adder of x, which is s, the full adder s output is equal to the exclusive OR of z of the exclusive OR of x and y. So we have proven that they are equivalent. That s is equal to x exclusive OR of y exclusive OR of z is equal to this Boolean function for s. Therefore, the full adder can be implemented with two half adders and an OR gate. Let's go to the binary adder. Consider a 4-bit binary adder. So the difference is the binary adder is the more general adder we're going to use to add any number of bits. We can have 4-bit adder, 10-bit adder, in general an n-bit adder, where n is the number of bits. Let's denote AI and BI as the input bits of the two binary numbers, and CI is the carry from previous bit addition of the numbers. We also let SI be the sum and CI plus 1 the carry input in the current addition. So try to familiarize yourself with the notations. So if you write down AI, this is the bit. These are our inputs. Okay. AI, BI, and CI are our inputs. But this corresponds to X, Y, and Z. It's AI, BI, and CI. And then our output is SI, then CI plus 1. So don't get confused with the notation, especially for CI and CI plus 1. So just notations to indicate. Let's
write down ci plus 1 and si here. This corresponds to c and this corresponds to s from our previous discussion of the full adder. But we add the subscript I and then I plus 1 since we will be adding more bits. For example, we have a 4-bit binary adder where A is equal to 1011 and B is equal to 0011. So we will try to add A and B where A is 1011 and our B is 0011. Where is our AI? Subscript I 3210. So this is our A0, A0, A1, A2, A3, and this is A3, right? And our B is, this is our B0, our A is 1011, our B is 0011. Subscript AI, A0 is 1, this is A0, A1, A2, A3. And this is B3. So we have the values for A, B, but for CI, our input CI depends on our inputs AI and BI. So we can't really, if we try to analyze this, we can consider CI as output actually because our original inputs are AI and BI. So we can consider this as an output, but in the name of adders being an adder, how do we say that? Since we're considering an n-bit binary adder, we are considering an n-bit binary adder, we know that for a binary adder, the outputs are the sum and the carry, not the carry that is caused by the inputs here, but the final, the final carry. CI plus 1. Okay. So this actually, the CI and CI plus 1 are very much related, since the output here is the output here actually is the input to the next stage of the adder. So EIBI, this is the output. We have an output carry from the addition, and then that carry will be the input of the next row. Okay. Hope you are not confused. This is
the block diagram or the logic diagram for the 4-bit adder. Can be implemented by using 4 full adders that we have discussed. Inside this full adder is this circuit, the full adder circuit, or this one. So we have one full adder, 2, 3, 4. The inputs are A, B for each bit of A and B, and then another input is the carry. Notice C sub O, that's the initial carry from the previous stage. For the 4-bit adder, C sub O, we would expect that to be 0 if we don't connect it from any other circuit. Then the output carry, we have the output S sub O, the sum, and then the carry will be propagated to the next stage. So that's how you implement a full 4-bit adder using full adders. We can extend that to have any number of bits. Say 10-bit adder, we need the 10 full adders to implement the 10-bit adder. Now let's try to analyze how the carry is being propagated. The addition of two binary numbers in parallel implies that all the bits of the gent and addend are available for computation at the same time. The total propagation time is equal to the propagation delay of a typical gate times the number of gate levels in the circuit. So from the previous examples or discussion, we assumed that this carry is readily available to the next circuit. We did not consider the propagation delay caused by the logic gates, but we know that we should in an actual circuit, we need to consider the propagation delay caused by the logic gates. If we have this n-bit adder, then we will how much is the propagation delay when we arrive to C4. So the total propagation time is equal to the propagation delay of a typical gate times the number of gate levels in the circuit. Full adder with B and G shown. What are these B and G? They are called for an n-bit adder, there are 2 n-gate levels for the carry to propagate from input to output. Yeah, because if we look at the circuit 1 and 2, there are 2 gates before 2 times n gate levels for the carry to propagate. We are concerned about the carry. Look at the carry here. Carry here. There are 2 logic gates, right? That's why for each full adder that we implement, we have 2 logic gates. So that's why 2 times the number of full adders, that is equal to n, the number of bits. So 2n gate levels. The carry propagation time is an important attribute of the adder because it limits the speed with which 2 numbers are added. We have already discussed that from the previous module. We need to consider the propagation delay of the logic gates. And here, the most important is the propagation delay of the carry because it will be the last output that is to be evaluated. It depends on the previous carry values. We know that, for example, this is our carry. This is the value of our carry. And this is our output. Let's say the delay we have this 2 nanoseconds delay for the output to be propagated. This is 2 nanoseconds, so before this time, the carry is not yet propagated. Therefore, we expect the output to be unstable at this portion. Therefore, we can't measure the output during this time, because if we do, we will get the wrong result. We have to wait for the signal to be propagated to the output. We have to measure the right output from this time going. To get the right output for the input in this time interval. So the right output for this time interval arrives at this time interval. That's how important the propagation delay is, so that we can measure the right output corresponding to the input. The carry propagation time is an important attribute of the adder because it limits the speed with which two numbers are added. Pi and Gi, P sub I and G sub I from figure 4.10 are Pi is equal to A exclusive or B, and G is equal to AB. So we just replaced the sum and the carry. We just replaced the sum and carry with P and G. Right? P corresponds to the sum, G corresponds to the carry. Well, the output Si and Ci are, let's sum the carry. Look at that. Somewhat the same. Pi stands for the carry propagate, and Gi is equal to the carry generate. Okay. So what we are trying to do here is to express the carry. We're trying to express the carry in terms of the propagation delay. So in terms of the carry propagate and the carry generate. Propagate and generate. We use the term propagate for the S, the sum, because we are just propagating. And Ci corresponds to Gi for, because we are generating the carry itself. Trying to generate. Somewhat hard to explain. Anyway, let's move on. Carry look ahead logic. Carry look ahead logic is the most widely used technique to reduce the carry delay time. So how can we reduce the delay of our carry? We have this what we call carry look ahead logic. how did they implemented the carry look ahead logic. This is the logic diagram of the carry look ahead generator. Continuing this P and GA values for I, we arrived at the circuit below in determining the carry C0 to C3. Let's check how it is being derived. So C1, C2, and C3 in terms of, they are in terms of P2, G2 is P2. Let's try to analyze the difference. What is P0? It's just the exclusive OR A and B. How about P2? So from this figure, what do we notice here? We have two logic gates. The propagation delay for the circuit from P2 to C3 is just two logic gates. The question is, what is this P2 and G2? Well, P2 is just B2 and exclusive OR B2 and A2. Okay. Then we connect this. The inside of this carry look ahead generator is this circuit. So there are two logic gates here. Two logic gates plus two logic gates. So P2 is exclusive OR of B2 and A2. Our P2 here is exclusive OR of A2 and B2, and it's just to get C3 is just ended with G1, and our G1 is just A1 and B1. Our G1 here is just A1 ended with B1. Therefore, the propagation delay of this circuit for bit adder with carry look ahead generator is 1, 2, 3. We know that there are two logic gates here, two logic gate levels here. So 1, 2, 3, 4. So there are actually 4 logic gate levels or delays for the adder. So we have improved therefore the gate delay of the carry from 2n gate levels to 4 gate levels. So if we have 10 bits, if we're trying to add 10 bits, if we don't use the carry look ahead generator, we will have 2 times 10, so 20 gate level delays. But if you are going to use the carry look ahead generator, we will only be using 4 logic gate delays. So the difference is 20 versus 4 gate delays is very, there is really a great difference or improvement. So what is the drawback with using the carry look ahead generator? The drawback is we are using more logic gates. I mean more, this is more, it will be more power hungry, and the area will be bigger because we are using more logic gates. So there's a drawback, but there is a trade-off between area power versus time, area power versus the speed of our digital logic circuit. Let's now go to the binary subtractor. Let's discuss this in part 2. Let's discuss this in the next video. Thank you for watching, and please subscribe.